Hi everyone, in this video we're going to go through the solutions to the second SAC. So I have scanned the solutions, hopefully they're not too bad. So I'm going to talk about them, and even though I know it's probably easier just to copy down what I've written, it's extremely important that you do understand the working out as well, or when you have to explain something, what was actually expected for that sort of question. All right, in question one, this was done quite well. So you had a parabola with some features given to you. So obviously you had to find the equation of the parabola. So the two main equations are just here. Let me just get my pen. So we've got this one here or this one. So either one was fine. I also think some people did, I shouldn't say some, I think there may have been one, maybe two, who gave it an expanded form, which was also fine. So just needed the equation of that parabola. So in leading up to your exam, it's extremely important that you know how to get the equation of a function given features of that function. So you can see there what I've done. What else was I going to say? I can't remember. All right, so what we're going to do with this question, sorry, I'm just thinking, approximate using left rectangles the area between the x-axis and the parabola between 2 and 6. So this was done quite well. If there was anything that was incorrect, probably not calculating the correct rectangles, so maybe doing right rectangles instead of left rectangles, maybe an incorrect substitution or something. But a question like this, you should just be defining it on your calculator and then just doing f of 2, f of 3, f of 4, f of 5, which are the points that your curve meets the left corner of your rectangle. So we had a width of 1, so substituting on all those values in. So we've done a lot of work on that. Not too fussed about spending a lot of time explaining that. There wasn't the expectation that you graphed it, but most of you graphed it, which was good. Some of you didn't do between 2 and 6, which was a little bit disappointing, just not reading the question properly. But if you did graph it and you didn't do the other working correctly, I still considered that. So don't think you had to get everything right to get any marks for this question. All right, moving along to question 2. So this time we've got a cubic and we've got some features of that cubic as well. So just always take note. Sometimes you've got a question that says passes through the origin. So there's one bit of information. We've got a maximum turning point at 232 and a minimum turning point at 60. So we're using those three features to find if we're setting up a cubic like this, A, B, C, and D. It's probably the easiest way to just do your cubic in expanded form. Now, obviously, if it's going through the origin, the value of D is 0. Okay, so we already know that. So that means we now have 3 unknowns, which is A, B, and C. So 3 unknowns, you need 3 bits of information. And I think there was a possible 4 bits you could have put in. So we've got our 2 points, 2 and 32, and 6 and 0, and then using the derivative. So remember, a stationary point, your derivative is equal to 0. So putting in 2 there, or you could have done 6 as well. Okay, so doing that on your calculator, we get A equals 1, B equals negative 12, and C equals 36. Now we've done a lot of these as well. So just doing it all on your calculator, you could have set those equations up and solved them by hand, but that would have also taken the whole lesson. So just making sure you use your calculator for things like this. There's nothing wrong with defining a function and then just using your calculator. All right, so what I've got here, let me just use my cursor, are basically 3 equations. All right, we've defined f of x, and I've already said what x is. So when x is 2, f of x is 32. Okay. Let me just think what we've got here. So we've got our function, oops, sorry. We've got our function in expanded form, which is this one here, or some of you did put it in factorized form, which is fine as well. I don't really care. And then we're finding the area. So for this question, we had to approximate using right rectangles, and we're going between 0 and 6 using 6 rectangles. So that means the width is 1, which you can see here, and all these substitutions are just finding the height of your rectangle. Again, we've done that quite a lot of times. So the area is 105. And I did draw the cubic as well, so a lot of you did draw it, which was fantastic. Yeah, and that was done quite well. You're not getting confused between your left rectangles and right rectangles, which is great, which is often an area of confusion, I guess. All right, so here we're getting a little bit, don't want to say tricky, but there's no single answer. All right, so you had to use a function or multiple functions to show that when approximating using rectangles, the approximate area gets closer to the actual area as the number of rectangles increases. So in marking this, I did substitute in your function and looked at your answers and then looked at your response. So you did have to respond to the question, I guess, with an explanation, and also support that explanation with, you know, the maths. So obviously many different answers, infinite answers. You probably all have different answers, but I'm looking for the comparison of at least 3 approximations. Now, I think that at most I've probably got 2. I can't think of anyone. There was probably some people who did 3, but I did need, was looking for 3, but if you gave me 2, that was okay. But you couldn't just have 1. So a comparison of number of rectangles and also giving me the exact area. So obviously that's what we're leading towards. So the actual area. So as your number of rectangles increases, it should get closer to your exact area, which is what it states in the question. And an explanation that refers to the above. So let's just quickly do a question. So let me just think of something. Let's do one that we did before, just because it's going to be easier for me to draw. Okay, so here we've got a cubic, and we've got 6. So we have 6, 1, 2, 3, 4, 5, and then the 6th one here, 6 rectangles. So if I increase that to 12, okay, so we've got our 6, let's just do the 12, and I'm doing right, so I need to do right again. This is where I probably should pause the video. Okay, I'm going to make a mistake somewhere. I probably should have gone from the right side. I'll do that. Okay. This is where I'm going to get stuck. There we go. Am I doing it right? Trying to concentrate. There we go. Do my steps and then I'll put the vertical lines in. Looks pretty good to me. Whoops, a bit wonky there. And I did do a question, a similar question. Oh, did I do that in half? I think I did. Leading up to your SAC, I did explain this. So I could kind of tell when marking the SACs who actually watched those videos, because if you watch those videos, you would have seen links with your actual SAC. So I did go through this probably in a lot more detail than what I am here. So if we've got now 12 rectangles, your little gaps are going to get smaller. So your over approximation is decreasing and your under approximation is increasing, so you're closer. So you can kind of see that. Now, I did 6 rectangles before here, So if I was doing the area, oh, go away, sorry, the area for 12 rectangles, obviously I'm decreasing the width of the rectangle to 0.5, and then, oops, I'm just going to do, the first one is 0.5, 1.5, and then I'm going all the way to 5.5. All right, so you'd do that on the calculator, and you then also should have had the actual area. So I'm just going to write that. We're going from 0 to 6. So you do the actual area as well. So you can use those 3 values, or if you had 3 approximations, that's good, to show that, well, as the number of rectangles increases, you're getting closer and closer to the exact value. So just going back to those points, what you had to show. So I said at least 3 would have been ideal, but most of you just did 2, so that's okay. The exact area and an explanation. So, you know, as I pretty much just said it before, and then you would refer to those values. And that was done, yeah, quite well, although a bit messy in parts. And some of you drew graphs as well. So that was always nice to see graphs, and not that there was much of an expectation, but obviously that would still give you some marks. So if you were lacking in one area, you did, I guess, regain those marks by having those graphs there. So that was good. So remember, it's you demonstrating your understanding of the content. So I'm not going to dismiss the graphs you drew as long as they're correct. All right, in question 4, use any function or functions you like to explain under what conditions you would be over approximating the area under a curve and when you would be under approximating when approximating using rectangles. All right, so again, obviously many different answers because you'd all be using different functions. But the things I was looking for, 2 different function or one function that increases and decreases. So what I mean by that is you really wanted to look at, well, what happens with left rectangles when they were used for a function when it was increasing, and what happens when that function is decreasing. All right, so obviously if you're using left rectangles, and let's go, I'm going to use my parabola up here. All right, so when the function is decreasing, actually I think I said that around the wrong way before, I can't remember. All right, so this is decreasing, all right? So remember your little ant is walking along, it's going up, so it's increasing here, and then it's going down, so it's decreasing. So when you're using left rectangles, all right, when the function is decreasing, and I've written this down before, later, so I'll show you that. So when it's decreasing, left rectangles. When it's decreasing, you are over approximating. All right, so you can see that here. All right, your little rectangles are hanging over that curve. But if we were to do left rectangles on the other side, and let me just get a bit more of a scale happening here. Oops, not very good drawing, but you get the gist. All right, you can see when we're increasing, we are under approximating. All right, so you did, sorry, I just need to concentrate on how to spell approximating. You did have to consider both when the function was increasing and decreasing, and consider both left rectangles and right rectangles. So let me go back to my dot points. All right, so where did I get up to? If you had another function, would have been good. I don't think anyone did, so I didn't really penalise anyone for that. I do appreciate that it was a lot to get through in one period. A clear explanation of the fact that when a function is increasing, left rectangles under approximate. whereas right rectangles over approximate, and then basically the opposite. So when a function is decreasing, left rectangles over approximate, whereas right rectangles under approximate. So I did want to see basically all of that or something similar to that in your own words, but you needed to have the maths to support that. So some of you drew graphs, which was great, but you also had to show that it was above or below, or over approximating or under approximating, by referring to the exact area. All right, now last question in the first session. So let me just read it. So use rectangles to show that the area between the x-axis and the curve f of x equals log base e x plus b, where b is greater than 0, is equal to the area of the y-axis. Oh, what a mouthful. Okay, so this question here, I didn't mind if you chose a value of b, and most of you who did this question just substituted in a value of b. So with my solution, I've just left it in the general form of b. I think there may have only been one person who left. Oh, some of you gave me the the inverse still in terms of b, or x and b, which was great. That's fine. If you did substitute in a different value, I didn't really penalize you if you did. So instead of using b, you said let b equal 2. But for most of you, when you were doing your proof, did not do what I did, and that's fine, because oh my god, this would have taken you probably quite a long time to do. So I just left everything in terms of b, and I think I use right. Okay, hold on. Let me just read what I'm doing. So for f of x, I use left rectangles between x equals 1 and x equals b. So we didn't really know what the upper limit was. Using 4 rectangles, and then basically when you're doing the inverse, you're then using right rectangles, and you're going from the y-axis. I'm just thinking now whether I've made an error there, but let's move on. Okay, so there's the two graphs. All right, so we've got f of x and the inverse. So remember, a function and its inverse is reflected along the line y equals x. So it's good that, oops, I was going to say it's good that I've got grid paper, but yeah, so they basically should be reflected along that line. Now, obviously, that point of intersection is a little bit out, but other than that, it's not a bad looking graph. Most of you who did this question were able to also draw that graph, and you did draw the rectangles in as well. So this question was done quite well, given that I thought it was quite a challenging question, but similar questions have appeared on past exam questions. So it's good to, I didn't like that line, that was a bit wonky. It's good to remember that if you had to find the area, actually, and this is in one of the later questions, if you had to find the area between the y-axis and a curve, so let's say this area here, remember that area is the same as this area here. All right, so even though you use rectangles in this question, I'm just showing you that that area is the same as this area here. All right, between 1 and b. Can't think of what else I want to say with that one. If you didn't answer this question and you want to write in a solution, can I ask, instead of writing down what I've put in, just let b equal something. All right, let b equal 2 or something like that. All right, and then it's going to be a lot easier for you to actually get your head around what is happening. But basically for this question here, just proving that those two areas are equal, which is a good question leading up to the exam. Wouldn't it be great if that was on the exam? All right, moving on. So this question here, you've done, or you should have done quite a few of these, or maybe with a rectangle, not with a triangle, prior to your exam. Sorry, not your exam, your SAC. Okay, so I did base this question on a past exam question. And it was done quite well. Just make sure when you've got to show that question, I don't want to see the answers straight away. I don't want to see this. It's not showing me that you understand the area of a triangle formula. So the area of a triangle is a half base times height. So putting that in, which most of you did, and then a half times k. So your base is this distance here, which is k. And then your height is this distance here, which is 4 minus k squared, and then multiplied by a half. So done quite well. And then some of you went on to find k, which was great. Just remember there were 2 solutions for k. But because k has to be greater than 0, k equals 2 root 3 on 3, or if you had 2 on root 3, that's fine. I just rationalize the denominator. So some of you got to that point and then stopped. That's not your maximum area. That's your value of k. Your maximum area has to be substituted into your area formula, or more specifically this one here. So you were given that in the question. Okay, so you substitute that in and you get an area of 8 root 3 on 9, which I would have preferred as my answer. But if you gave me the approximate with decimals, that's also fine. But just remember, this is a really complicated answer on your SAC, but leave it as an exact value, but definitely on your exam, leave it as an exact value unless it specifies to round it, okay? You would hate to do lots of working. A question like this, probably worth 2 marks. And if you go from 8 root 3 on 9 to the decimal, you've lost your mark. All right, so you need to leave it as an exact value unless it says otherwise. All right, question 1b, explain what happens to the dimensions of the triangle as the function f of x undergoes the following transformation. So function notation here. So m times f of x, m is a dilation of m from the x-axis, and f of nx is a dilation of 1 on n from the y-axis. So they're your 2 transformations, and most of you did that well. Some of you just wrote n here. It should be 1 on n. All right, so when you answered this question, obviously m isn't always going to be positive. If you said when m is negative, that's great. But because, actually it's fine. If you said m was negative, that's fine. And I haven't mentioned it here, but if you did say it was reflected, that's great. When m is greater than 0, the height of your triangle increases. So you're getting stretched away from the x-axis. Now, a couple of you did say that also changed the base. It doesn't change your base. So your triangle, and I did explain this in a video prior to your SAC. All right, so let's say that's your triangle. If we're increasing the height, all it's doing is, oops, a bit wonky, making the triangle really bad. Should I try to make it a little bit straighter? A little bit better. Okay, so your height just gets longer, but your base stays the same. Okay, so you are also increasing the area, but you didn't have to refer to the area. Now, when your value of m is between 0 or 1, so actually I shouldn't say some, I think one person said it was a fraction. Just remember, fractions can also be greater than 1. So notation like this is preferred over saying a fraction, because a fraction, that's a fraction, but clearly I think you meant somewhere between 0 and 1. Okay, so that decreases the height of your triangle and would decrease your area. Now, when n is greater than 1, the base of the triangle decreases because remember, your dilation is 1 on n. So your base decreases, but your height stays the same. And then if n is between 0 and 1, your base of your triangle increases. So I'm just trying to think. Yeah, I'm not going to show you. I was going to show you on Desmos. But yeah, most of you answered that question, just made a few incorrect statements. So just make sure your statements are correct, and using notation like this, all right, for your values of m and n. And I probably in my answer should have considered when m and n were negative as well, because I didn't state in the question that they were greater than 0. But yeah, when they could have been reflected also. All right, number 2. So this was done really well. I was really, really pleased with this, considering that, well, we did do some questions from past exams, but you know, you were relatively new to definite integrals. So you could do this quite well on your calculator. All right, so you had to do 2 methods. I did see some people, though, approximating the area. Okay, you did have to give the exact area. So if you use rectangles here, we're not approximating, we're finding the area. All right, so I think I've got 3 methods you could have done, but so the 2 first ones are probably what most of you did. I don't think anyone actually did the 3rd method. So you could have said, all right, an area of a square. So this is 4, it's a bit hard to see, and this is 4. So you could have said, all right, there's my square, a 4 by 4 square, which is here. So the area of that is 16. And then I'm going to subtract this area here, and then I'm left with that shaded area. All right, so area of the square minus the area below the curve. So most of you did that, which was awesome to see. The second method, the area of the inverse of y. So this is what I was saying before when we did that other inverse question in the first session, that when you're looking at the area between the y-axis and the curve, you can also just do the inverse. So I did see some incorrect notation for your inverse, so please make sure you use the correct notation. I would hate for you on your exam to lose marks just because you couldn't write f of -1 of x. All right, you need to have the correct notation for inverses. So your inverse was x squared on 4. It's a bit hard to see there. So just setting up the definite integral there. So most of you use those 2 methods, and now you know, we've also, since your SAC, learnt this method, but I thought maybe someone who had gone ahead may have seen, all right, if you're looking at the area between 2 curves, or 2 functions I should say, because y equals 4 is not a curve, it's a straight line. So you've got there your straight line going through y equals 4, and then minus your other function. So there it is there, 4 and 2 root x. So basically what we were doing here though is, you can see there's 16, is that's the same as calculating the area of the full square. Okay, so it's just the difference between the 2 areas, which is what we did in step 1, but that's, I guess, the definite integral notation for it. Okay, but done quite well. I was very pleased with that question. All right, question 3. Now this was put on, I guess, to challenge you girls, but it was done really well by those who, so if you got this correct, it was great to see, because we, again, hadn't learnt how to do areas like this, but this is where you've got to think, like in an exam situation, or obviously in your SAC as well. It's like, well, what could I do to that graph to answer it? And it was good to see some of you actually realize, well, I could actually bring that whole graph down 6, so that what's happening with your curve is, well, this turning point here obviously goes down 6, and this one here goes down 6. So, and we're going through 0. So I want to try to draw it as accurate as possible, but I'm probably not going to. So it's just shifted down 6. I don't know how I'm going there. So this shaded area here is now here. And this shaded area here is now here. So this is your x-axis. So now it's turned into a definite integral that you're more familiar with, okay, because we had not done this. So on your exam, and main purpose of putting this question on was to get you to see, well, okay, it's a little bit different to what I've seen before. What skills do I have to be able to answer it? And you should know that you can lower functions. So this one here, we can just subtract 6. So I'm going to make it a little bit bigger so we can see my working out. So the very first method I've got is shifting your cubic down 6. So you can see the cubic function g of x, and then I've subtracted 6 from it. So I defined a new function, h of x, and there it is there. Okay, so it's my cubic just shifted down 6. Now, obviously, when finding that area, you did need the x-intercepts, and some of you found these values, which was great, not as x-intercepts, but the intersection of the two lines, of the curve and the intersection of g of x and f of x. Okay, so the same points. So if you did that, that's great. I still awarded you points for that, marks, even if you weren't able to do other things. Okay, so I've just set up the definite integral there because h of x was already defined above. I didn't have to write it again, and I'm just doing it on the calculator. That would be quite a messy one and a long one to do by hand. So we've got the area on the top minus the area on the bottom. Okay, and there's a subtraction here because it's below the axes. Okay, obviously I'm adding two areas together, but because this area, let me just go back up, this area here, oh well, this one here, is now below the axes. That's why I got a negative answer. So just to compensate for that, I had to put a negative out the front of my definite integral. So I get a positive area, so 46.665. And because I was so excited to see people get that answer. I was so pleased because I thought, yeah, it is a challenging question. Okay, so seeing that -6, some of you doing that was great to see. Some of you were able to find the area. I think this, I'm drawing a lot on here, this area here. Yeah, so that was still good to see. All right, obviously not entirely correct, but you know, the purpose of the SAC is to demonstrate what you know. So it was good to see that you could still find the value of, the area under the curve. All right, so the second method is adding the two areas. So just trying to figure out what I did here. Adding the two areas. So area 1, okay. So I've got g of x minus 6, which was f of x. And I can't rub this out, I'm sorry. So to work out this area here, you could do that area up the top of the whole thing minus the area below it. Getting a bit scribbly here. And then area 2, you're basically doing it the other way around because now f of x is above g of x. Yeah, so you get the same answer that way, but I'm just trying to think if many people did it that way. I think I did see a few people do it that way, but it was mostly that shifting down that I saw. All right. The video wasn't as long as I'd thought it might be, which is great. But girls, please make sure that you understand what was happening in this SAC because these questions were based on a lot of past exam questions, and you know the likelihood you're going to see similar questions at the end of the year, it's going to be quite high. All right, so make sure you understand all the components of this SAC. All right, girls.